Hi and welcome to this video where we're going to have an inferential statistics review. So I'm not going to look at any examples in this video. If you want to look at some examples, I've linked a video in the description below which just goes through the exam questions. There are videos which are under the inferential statistics playlist which do a combination of both. So as part of inferential statistics exam questions, we can be asked about populations and samples, the margin of error, parameter versus the statistic, central limit theorem, the empirical rule, confidence intervals, and we have two that we need to know for higher level. The first one is confidence interval of the mean, and confidence interval of the proportion is our second one. We will look at hypothesis testing, and finally we will look at p-value. So let's talk really quickly about populations and samples. So when we want to gather information, it's not always possible to work with the full population, and the population is the group that we want to know more information about. It can be very time consuming and expensive. So the alternative is to use a sample to work with that represents the population. Okay, but when we do this, the practicality of using a sample means that we cannot equate the results from a single sample with those from a population. So what that means is mu, the mean of our population, is not the same as x bar, the mean of our sample. So just because I take a sample, the sample does not exactly represent the population. It'll give us a good idea about it, and we can infer some information about the population using the information we have in the sample, but we cannot say that mu is equal to x bar, and that's really important. And when we use the central limit theorem, that's what we're going to be trying to overcome, this idea that mu does not equal x bar. Other ways that we've overcome this, if you've not already revised, is looking at using confidence interval, creating confidence interval, and those videos are all linked below. And there is a full inferential statistics video that goes through everything within the inferential statistics course. So just a quick reminder, mu is equal to the mean of the population, x bar is the mean of the sample. So we already know that mu is the mean of the population and x bar is the mean of the sample, but I'm going to give you two new words now. So mu is actually called a parameter and x bar is called a statistic. And what that means is a parameter is a numerical property of the population and a statistic is a number of property of a sample. So we have seen in mock questions where they've kind of pulled these wording around a parameter or a statistic, and just so you're aware of what they mean, there's our definition here. So a distribution of sample means, so different samples give different means, but the distribution of sample means is normal for a large sample size. So what that actually means is, imagine I take my population and I take loads and loads and loads of samples, and for each of my samples I record x bar. And if I start recording those x bars, what I should find is the bigger my sample gets, the more like the normal distribution that these sample means will act. So what I get is something like this. If I take a small number, it looks a bit all over the place, and then I look a slightly bigger number and a slightly bigger number again, and what you can see is as n gets bigger, that means that the actual distribution sample means is looking more and more like the normal distribution. And this is what we call the central limit theorem. So I saw the central limit theorem described as this one, so I thought it was very nice. So it's called statistical magic, and that is what it is. And as we work through it, and you'll see what the central limit theorem allows us to do. It is a bit of statistical magic. So the central limit theorem states that if a random sample of size n is taken from any distribution, and that's important, any distribution with mean mu and standard deviation sigma, then provided n is large enough, we can say that the x bar, so the distribution of sample means, is approximately normal with mean mu and standard deviation squared of sigma squared over n. So just to help you, what we get in this notation is mean and the standard deviation squared. Standard deviation squared is our variance. We don't really talk about variance at Leaving Cert higher level. So we can think of it just as standard deviation squared. And it's so important because in real life we don't always know the distribution of the population. And I suppose we focus so much on very basic distributions. If you think about what we know the normal distribution. We've talked about the normal distribution a lot. Other than that, we've really only talked about either skew to the right and skew to the left. They're the only distributions we've had. So it's really important that if we have a random population that has some distribution that we don't know, that we can use the idea that if n is big enough, that we can basically use the sample as being normal or approximately normal. And when we deal with normal distributions, it means we can work with our log table. So here it is again, and I just want to point out that sigma squared over n. I said that was standard deviation squared, but where is it coming from? And it's coming from our log tables, and you might recognize it. It's the standard error of the mean or the standard deviation of the sample means. It can be called either of those things, and it is that squared. So it is the standard deviation of the sample mean squared, and that gives me sigma squared all over n, and that's this part here. The second thing that I suppose to point out here is our last statement here, provided n is large enough. And that is kind of like a condition, but we need to look a bit more about that. So for most situations, n equal to 30 will be large enough, and that is, once the sample size is greater than or equal to 30, the sample can be treated as a normal distribution. So this means we can use page 36 and 37 in our log tables. So that's the page that we care about. So it doesn't matter what kind of distribution, it doesn't matter the distribution of the underlying population. Once I have a sample of 30 or more, I can use page 36, 37 for the sample. So our magic number is 30. So that is, when we say large enough, we're talking about the sample size of 30 or more, and it's really important that you have that in your head. So the empirical rule has 3 individual statements, and all 3 are displayed here, but I'm going to give you a little summary on the left as we go. So the first one is, there 68% of the data that sits between one standard deviation either side of the mean. So that is mu plus or minus 1 standard deviation. They then, the second part of it is 95% sits between plus and minus 2 standard deviations, and the third part is 99.7% of the data sits between plus and minus 3 standard deviations of the mean. So that is nearly all of the data sits between 3 standard deviations. There's 0.3% that doesn't, and that's 0.15 in either tail. So that's so tiny. Just a little note at this point is here, for higher level, we don't generally talk about 2 standard deviations, we actually talk about 1.96. But this empirical rule still says 2, but as we get into the inferential statistics, we will be looking at it as 1.96. So now we're going to talk about margin of error. So when we use the sample, which is only a representation of the full population, we will have less accurate information than if we use the full population. So hopefully we can all agree on that. And another thing to note is the bigger the sample, the more accurate the information becomes. It's like an experiment in probability. The more times we do the experiment, the more accurate it becomes. So how accurate we are depends on the size of our sample. We will get an answer, give or take a slight error. So some of the things that I talk about with regards margin of error is, in English we talk about give or take or in or around, and it means we get a number, maybe a time, for example, so in around 10 a.m. That doesn't mean you're going to expect that person exactly at 10. It might be a little bit before, it might be a little bit after, or give or take. So somebody might ask you, how much did you pay for that top? And you might say, oh, give or take 20 euro, or in or around 20 euro. So we use it often if we're not 100% sure, and that's what we're going to look at here. So the margin of error is that give or take. So when we take any information from the sample, it's going to be kind of accurate, give or take some. And that give or take is linked to the margin of error. So the margin of error can tell us how valid or how much of an error there will be because we're using the sample. And the formula is given as E, the margin of error, is equal to 1 over the square root of n, where n is the sample size. And the only thing I would say about this formula is it's important to note that it's not in your log table. So it is something that needs to be learnt off by heart. And they have asked it, and we will see how they've asked it in questions. A lot of the questions we're going to deal with will be past papers, sample papers, and mocks. So let's talk about 95% confidence for a second. So for the Leaving Cert exam, we're just going to focus on 95% confidence. All questions relating to samples will include that we're dealing with 95% confidence to make them mathematically correct. However, we will never have to deal with any other confidences. Okay, so don't panic. A lot of students will often ask, but what happens if it says 99? And the answer is it won't. Okay, as you go on and study statistics in more detail, you'll see other things appear, but for the moment we're sticking to 95% confidence. Now, these are not the mathematical definitions of 95% confidence. This is just a way to help you to grasp what's going on. So, when we talk about 95% confidence, this can be very roughly translated as a 95% chance my information is correct. So, 95% chance I'm correct. We then will see 5% significance. So this is just another way to say 95% confidence, and roughly translated it means a 5% chance that my information is incorrect. Okay, so think of it this way. If there's a 95% chance I'm right, there's a 5% chance I'm wrong. And that's basically what the 95% confidence and the 5% significance are saying. One is saying just the same thing as the other, just in a different way. The margin of error that we looked at only works for 95% confidence, and dealing with 95% we use a z-score of 1.96, which we would talk about as rounding to 2 with regards to the empirical rule, but we are a lot more accurate now. We're actually going to 1.96. So our tail looks, or our normal distribution looks something like this. So because we're not taking either tail, and we just figured out in the last go that the one on the right was 2.5%. Because the normal curve is symmetrical, the bottom, what's less than negative 1.96, will also be 2.5%. And we end up with this two-tail test where there is 95% of the data between negative 1.96 and positive 1.96. So we're always going to talk about this in terms of a two-tail test, not a one-tail test. So just to be aware of that now and have this kind of image in your head. A lot of things we're going to do is going to relate back to this specific image, the idea of 95% in the middle and the 2.5% either end. So that's the 5% incorrect, the 5% significance. So let's talk about the 95% confidence interval of the population mean. Now, I've highlighted the word mean because for this, there are two confidence intervals. So we'll have a second one in another 2 slides. So just be really clear that this time we're talking about the mean. So using the information we know about the sample mean, x bar, we can create a 95% confidence interval for the population mean, mu. So let's think about what that means. 95% confidence interval. So I'm going to create an interval, so 2 numbers, where I am 95% confident that my population mean sits between them, or the probability of my population mean sitting between these two values is 95%. So this gives us a good indication. Remember I said earlier that actually when we use a sample, we are not going to be as accurate as the population mean. So it's not okay to say that the sample mean will be the same as the population mean. However, we could say the sample mean, give or take some, will give us a good estimation for the population mean. So the range of values that we are 95% sure that the population mean mu sits between. So to create this range, we're going to use what's called the standard error of the mean that we find on page 34 of our log tables. So it's this one here, standard error of the mean. So it is sigma of x bar, so that is the mean, equals to sigma standard deviation all over the square root of n. Now, that square root of n is hopefully something that you recognize. It's linked to the margin of error. Now, when we use the standard error of the mean, it effectively replicates standard deviation for the samples. So when we deal with standard deviations, we want to know, well, how many standard deviations are we talking about? When we talk about 95% confidence, we are talking about the z-score 1.96, and remember that the z-score means how many standard deviations. So this is what we're going to have. We're basically going to start with x bar, which is our sample mean, give or take, plus or minus, 1.96, because we're in 95% confidence, so we're talking about 1.96 all the time, and then we put the standard error of the mean. And that is how you create the confidence interval of the population mean. Now, I'm going to rub this out, because that is going to give us a plus minus, but I'm going to give you something a bit more eloquent, and it's going to look like this. So it's x bar minus 1.96, sigma over root n is less than or equal to mu is less than or equal to x bar plus 1.96 sigma over root n. Now, some questions also come in, depending on what book you're using, you may see that this is just a less than symbol and not a less than or equal to. Based on the material provided by Project Maths, there was an and equal to given in that PowerPoint, so I would follow that, and I'm going to give an and equal to. My thinking behind this is it links very much to when we're talking about z-scores, and with z-scores we will generally have a less than or equal to as well. It'll be negligible with regards less than or equal to. With regards what has already been asked on the paper, they have shown both less than symbols and less than or equal to. So I can't imagine anybody being penalised for either. So just if you have this slightly different, that's absolutely fine, but I'm going to stick to the less than or equal to as we work through it. So now we're going to talk about the 95% confidence interval of the population proportion. So just like with the mean, we can use the information we know about the sample proportion, p hat, to create a 95% confidence interval for the population proportion, p. This is a range of values that we are 95% sure the population proportion sits between. To create the range, we're going to use the standard error of the proportion that we find on page 34 of our log tables. However, because we don't know p, the proportion, we're going to use p hat instead. So what that looks like is, for the 95% confidence, we are going to start, I'll work it through and then I'll give it to you properly. We'll start with p hat. So that's from the sample, it's the proportion, but we know that the proportion from the sample is never going to be as accurate as the actual population. So it's going to be the proportion give or take. Give or take, so that's going to be plus or minus some piece. Because we're dealing with 95% confidence, we're going to talk about 1.96, and the piece in this case, so give or take 1.96 times this piece, that is going to be the standard error of the proportion. Because I won't know p, I'm trying to do the interval for p, we're going to use p hat in this formula instead, and it will look something like that. Now, when we actually break it down, I would advise you to write it with less than or equal to signs, and it will look something like this. So p hat minus 1.96 times the standard error of the proportion is less than or equal to p is less than or equal to p hat plus 1.96 times the standard error of the proportion. Hi and welcome to this video, which is covering hypothesis testing, which is part of the Inferential Statistics section of the Leaving Cert Higher Level course. So within this video, we are going to look at 3 different ways which hypothesis testing can be done. But before doing it, I would strongly recommend that you have already revised Z-scores. To help, the video for Z-scores has been linked in the description below, along with the full complete Inferential Statistics course video. So doing hypothesis testing, we talk about the null hypothesis and the alternative hypothesis. Now, this part is so important. This will never change, and sometimes students really get bogged down in the idea of what the claim is, and the claim is the null hypothesis, and that is not true. The null hypothesis is always the idea of no effect or null effect or no change. So it will always be mu equals or p equals, and that will never change. It'll be mu equal or p equals. So the hypothesis test will be on one parameter or the other, and whichever one it is, that's what we'll use. The alternative hypothesis is then always the opposite to the null hypothesis, and that's to ensure we capture everything. So for example, if I said mu is equal to 100, the opposite of that is mu does not equal 100, and that covers everything. So it'll cover every single value. So it's either 100 or it's not 100. So we're kind of looking here about an exhaustive event. In this sense, we go back to probability, the idea that the probability of all of these would add to 1. So it's either going to be one or the other. So hypothesis testing of a mean value. So looking specifically at the mean as a parameter, there are 3 methods. So using the confidence interval, using z-scores, using p-values. And if we want to test for p, this is the only way to test p. And remember, p is the population proportion. So we only have one method. So 3 methods for testing the mean, but only 1 for p. Now, we'll work through these and we'll talk about when a specific method is favorable over another. What I would say is it's usually down to method 1 and method 2. We would never use method 3 to actually do a hypothesis test, because method 3 relies on already doing method 2 effectively. You need your z-scores. So you might question, well, why would you ever need p-value? And what has happened is, because nobody would ever choose to do them, they are added in at the end of a question, as in what is the p-value of this hypothesis test, and to comment on it. So it is really important, and because we don't have a choice when we get. So let's talk about z-scores. So using z-scores to test your hypothesis is a very useful method, especially when you've not already created a confidence interval. So in the previous example, we saw that we created a confidence interval and then used it. So if we didn't already have the confidence interval created, is there an easier method? In my opinion, z-scores are an easier method. So since we work only with 95% confidence or 5% level of significance, we always compare our z-scores to 1.96, and that is a plus and a minus 1.96. So that's going back to what we would have learned at the very start of our inferential statistics. And in order to calculate a z-score, we have a formula that's very similar to our standardizing formula that we would have seen before. And this formula is on the top of page 35, and it's called the one sample z-test. And it's just underneath the heading that says hypothesis test. So that is z is equal to x bar minus mu all over sigma all over the square root of n. So some things that give us a hint that it's about a sample. Well, in its name it has sample. X bar implies the sample mean, and n implies the number in the sample, so the sample size. So let's take a look at using that. So the final thing we're going to look at with regards to inferential statistics, it's the p-values. So p-value itself stands for probability value. So this is the probability of getting results at least as unusual as the observed mean, given that the null hypothesis is true. Okay, now that is great, but can you understand what that means? So we're going to really break down the p-value so that you understand it and you can make a much better attempt at approaching these questions. Because often what I find with p-values, students really struggle and tend to learn things off. And once you start learning things off, it doesn't make any sense. You just get absolute rubbish in these questions. But basically, in simple terms, the p-value will give us a percentage which we can compare to our standard normal distribution. So let's take a look at our standard normal here. We have a set of possible results. We have very unlikely observations here on the left and on the right, and the true value of the null hypothesis and most likely observations are there in the middle. So there's a 95% statistical significance threshold, and this is important because this one here, that's basically 1.96, and there's a matching one that is just about here, I think, and it's minus 1.96, and everything within that is good. So I'm going to do this in kind of a green color. So this is good. Everything in there is what we want. And these outside pieces, these tails, these are what we call the rejection region. And this rejection region is what we're going to focus on when we talk about our p-values. Now, we've already talked with regards this shape and 95%. So let me go back to this idea. I have, change color, 95% of my data here, which means there's 5% in the tails, which means down here is 2.5%. And here is 2.5%. But we're going to work with our tails together. So with our p-values, we want to compare our answer to the standard normal distribution, which is here on our left. Since we're dealing with 95% confidence or 5% level of significance, we want to ensure that our answer sits inside the middle 95% of our data. So basically those z-scores, those minus 1.96 and 1.96, we wanted to sit between those, and that's where we're 95% confident. They sit outside those. That's getting into our 5% level of significance. That's where we're kind of worried we're wrong, because it's in those tails. It's in those areas where we're not sure. We really don't think that's going to work. They're what we call, remember, our rejection regions. So if the p-value is less than 0.05 or 5%, it means that it's sitting out in our tail. So if it's less than 5%, we're going to think of it as being out in that rejection region. If it's greater than 0.05, that means that it will sit in the main 95% of our graph, and we fail to reject it. Okay, so if the p-value is bigger than 5%, it's beyond our tails, because remember we only have 5% between our tails. So if it's bigger than 5%, it's going into the middle, and that is good. So we're going to talk about calculating the p-values, and just to say before we start into this, that this is a very mathematical way that we're going to go through it. This is really kind of what you would see in the workings. However, I find that students often struggle with this to understand it. So as we're going to go through the example, what I'll do is I'll use a very visual picture, like we would do with all of our z-scores, to really try and understand what's happening. I would definitely be using a more picture-based or a diagram method as you're working through the examples, just for yourself to use, so you can really get a sense of it. I think learning off these kind of formulas not going to be hugely beneficial unless you really understand what's going on. So to calculate p-values, we must first have the z-scores. And I did say earlier that actually we would never use the p-values for hypothesis testing, because if I worked and got the z-scores, if I wanted to do p-values, I'd first work and get the z-score. So if I got the z-score, would I not just go straight and compare the z-score to minus 1.96 and 1.96? So this is why they asked this question specifically as an extra question, a follow-on piece after you've done hypothesis testing. So in order to calculate our z-score, we must first use the one sample z-test on the top of page 35. So we've seen this a few times now. And then we work from our tables and we work out 2 times 1 minus the probability the z is less than or equal to the z that we've just worked out. So from page 36 and 37, our log tables, we know that we have the standard normal tables. We're going to use 1 minus the probability to get the right of our z-score, so to get the tail, and we're going to multiply it by 2 because we want to double it. So remember, our rejection regions, plural, they are each of the tails. There's 2.5% in each tail, so to get our 5% we would have to double one of the tails. Now if that seems like I haven't a clue what's going on, that's absolutely fine. Wait till you see the example and hopefully it will make more sense.